All right. Hey, so it's week 10. This is lecture 19, and we're on to electric vehicles. And if there's anything, do you want to cover anything at all from previous weeks? So I know Tim was kind of catching up on some of the other problems, and I think at this point, the solutions are there. If there's any solutions I need to launch, I can, just let me know. But otherwise, I'm just going to dig into the week 10. And we're only going to spend about 15 or 20 minutes here in the class, and then we're going to go out and take a look at the electric bug.
Okay.
Yeah.
Cool.
Does that sound good? Like a plan? Okay. All right. Week 10. So here's the reading assignment. Chapter 10. Take a peek through that guy right here. So I really like the way Brian set this course up. I mean, he just follows by the book. Week 10, Chapter 10, electric vehicles. So he goes through different types of motors, goes through the different types of power. I especially like that power equation right there, motor efficiency, compound motors. Goes through batteries, lead acid, cell voltage, nickel zinc, nickel cad, nickel metal hydride, motor controllers, charging stations, all the different vehicle tests, regen braking, rolling resistance, the mass of the vehicle, applications, benefits. Electric vehicles are noiseless. It's a good thing, but not so much if they're sneaking up on you. Man, that's something. And then challenges. One thing it says here, the cost of EVs is high compared to contemporary gasoline diesel cars. They're coming down all the time. And when you do the math on the dollars per mile, they crush. I mean, it's something like 2 to 3 cents a mile typically for energy. I've seen, versus double or triple that for gasoline. Driving range, limited seating space. We'll see that here with the bug in a little bit. And then consumer acceptance and satisfaction. And I think the reason there is just that there aren't enough of them, yet. But the hybrid, though, the Prius, I think its reliability is finally reached the point where pretty no-brainer to buy one. All right, let's just take a look at Kern's notes. These are going to be the things that are important for the exam.
That's electric?
Fully electric, yeah. Glenn Kreisel here owns one of a couple Tesla Roadsters in town. We're pricing them out. I think it's the Model 3 that comes out next year. They're $60K up front, but I think the model that Tesla's put together is that refueling is free at any of their stations. You plug in and you're not paying for it. So the cost of the energy is built into the upfront cost of the vehicle.
And the modular lithium ions, that's going to really drive the price down and make it more reliable as far as the whole battery doesn't have to be replaced.
Mm-hmm.
You can just replace the module.
Yeah, the one Glenn had, it had 8,000 individual cells, and that was their kind of their little breakthrough, is that we don't want one giant battery, because if it dies, the whole thing dies. So 8,000 cells, each with its own temperature monitor. The nice thing about the Teslas is every single aspect of the car that is allowed to be electric is. The only two things that have to be manual in a car, according to DOT, are the glove box. You have to have a mechanical switch on the glove box, and the hazard lights has to be a push button. Everything else is electric, and so they can download new software for their battery charger, charge controller, motor, and even a lot of these have the self-driving features. So they've ways to detect the white line. I don't see a double yellow, but that's becoming pretty common even on, like this 2016 Subaru Outback has that. Then also ways to sense the car in front of you so you're not rear-ending. Then once these start talking to each other, just drive along in very tight formation. A lot of big truck companies, Mercedes is going this way now with their big trucking fleets, where they just bumper to bumper these things, dial them in. Maybe one guy's in the front driving it with like 10 other trucks right behind him. And so the gas mileage is greatly increased near the mileage.
Make sure you got your off-ramp way ahead of time.
Yeah, yeah.
You know what I mean?
Yeah.
You're on the freeway, try to get through that stud tree.
Yeah. So pollution-free, really the pollution aspect is in the battery recycling. So as long as these companies are doing cradle-to-cradle analysis, I mentioned Subaru a second ago, they have zero landfill facilities. They recycle everything. The engine efficiency, we've talked about Carnot efficiency before. The Carnot efficiency is limited by the temperatures. The engine efficiency or the motor efficiency is 80-90% in electric vehicles. Lower maintenance costs, there's just fewer parts. Fuel pumps and timing belts and all that kind of stuff, you don't need that anymore. I mentioned lower fuel costs, energy costs, 2 to 3 cents per mile. The battery is the kicker. I also mentioned the fact that Tesla did a lot of small batteries rather than one big one. Another thing, too, is the cars themselves sort of act as a grid stabilizer. If you get this thing talking to the grid, you could even see it as a way just to dampen voltage. What's up, Gary? Hey, the magnets came in. We'll grab them.
Sweet.
Here in a little bit. I'm not going to do a whole lot in lecture today. I want to get out and take a look at the cars.
Problem for your battery.
What's that?
Battery problem.
Good.
Rectifier. Get this.
Oh, nice. So as I mentioned, Tesla set the bar high. The reason the lithium-ion batteries are sort of winning the day, let me show you this little chart on energy density. Wikipedia's got a nice little site here, and we can just look up the energy densities of lithium-ion versus lead acid. Okay, here it is right here. And I know Tim covered hydrogen last time, so hydrogen's way out here on energy per unit mass. Lithium-ion, I don't even see, I don't even see lead acid. I don't even see lead acid on here. But as you can see, the lowest energy density, at least on a megajoules per unit volume, and that's why a lot of times some electric cars, you're losing space because the battery is taking up this the actual volume in the car. Okay. 3.5 hour charge time can also be a setback. I was there in Bozeman, and there was a woman just kind of parked at the wasn't the Holiday Inn, but one of these hotels there in Bozeman, charging at the station. And it took some time out of her trip, but it also looked like she was just getting some work done sitting there with the charge. And I think they're also working on swappable battery packs. Here's some other notes. So here's Toyota. Air pollution, obviously, big deal. This must have been a picture that Brian Kearns took 3 years ago. Have you guys seen this movie, Who Killed the Electric Car? You might take a look. It's a lot of times when I say, like, who killed the energy tech program, I reference who killed the electric car. Because there's a lot of factors. I mean, you have to build them in, mass produce them. Someone has to buy them. They have to be, safe, reliable. So there's a lot of different moving parts to get something, this big into action. But I think we're at the point now where I think we're really turning the curve on that.
Tesla
Turning the
built an
corner.
electric car, because he died without making.
Nikolai Tesla.
Killed the
Oh,
electric car, because he died without making wireless energy transfer possible.
okay. Tesla wasn't brought up, but I heard the new Tesla. There's a new Tesla movie or documentary out now. I think there was.
I don't know, I know one of his predictions, and some math that he was doing, kind of like stated that it's possible to have a wireless connection of electricity.
Yeah.
Oh, yeah, there is, definitely.
Well, you have lightning.
It's based in two-air energy, yes.
Well, my phone charges wirelessly. I just
So,
send.
do you have the little wireless hookup that you make, and you wrap little coils around it and walk like 10 feet out and you see it pumping through?
No, but this just sits on the charging pad and goes. I mean, that's how it.
No, I mean actually disconnected from the charging pad. You can walk away from it.
Oh.
I've seen it on YouTube video, I'm like, I don't know.
Yeah,
But
everything's got its
you-
range. But it's not. I mean, it's just it's a little transformer. That's all it is. There's a.
It's exactly what it
Yeah.
is. Because all you have to do is you take your connector, your little dock for your USB port,
Mhm.
you cut it in half and you open the wires up, you splice them down, and then you wrap your.
And if I'm not mistaken, I think the charging station for the bus is wireless. There's no plug. I think when the
No,
new
that's a,
the new
it actually comes up underneath and
Yeah.
connects up in there somehow.
yeah.
It's like the third line, the third track in a subway system.
Yep. For the new electric bus that the university got to, I think it charges.
Nothing you can get between point A and point B.
That's a charge.
Because the ionic dispersion is that's what, that kind of like.
Give you a little
laser
jolt,
based
make
on
your picture
that.
stick up.
Yeah.
That physics is just, get into that tube, you're getting vaporized.
That's a charging station for that bus, that one over there by the music building?
Yeah.
I think so. I haven't seen it yet, but yeah.
That's Royce Easton's way of showing the public, hey, look, I'm doing all I can. Give me some more of your oil money.
So this is kind of a cool story, though, that a lot of the Toyota RAVs that were originally made are still were saved from the crusher.
Santa Catalina. Sweet.
Mm-hmm.
Nice.
Yeah.
You got it?
It's not done yet, but you can go through it.
Yeah, I mean, look how simple that dash is.
I got a quick question. So a transformer
Yeah.
is like a solenoid? Because an electromagnetic inductor, that's what a solenoid is, right?
Usually a solenoid has a permanent magnet in it, but a transformer does not. A transformer, you just have two sets of coils, a primary and a secondary, and so the secondary coils are picking up the EM field, transforming it from high voltage to low voltage. Whereas a solenoid typically will have a permanent magnet that physically moves to open or close a switch. Where
Like an alternator has a permanent magnet too. I mean, they all have permanent magnets, don't they? They're not
Alternator.
replaceable. Why would they make the distinction between permanent and replaceable?
I'll tell you the distinction. I'll show you the distinction. So in a transformer, you have this is just a copper wire over here, and electrons are flowing through it. Then you have another one, and electrons are flowing through it. And then there's also typically a this whole thing is inside I think there might even be some here in the classroom. This thing's sitting inside a magnetic, or not a magnetic, well, it's magnetic, but sitting inside a metal frame. And the metal frame in the transformer is basically just keeping the electromagnetic field local. But there's no magnet here. There's no permanent magnet here. It's just two wires and wrapped around some metal. And so when and you know that the electric field is always perpendicular to the magnetic field. So the magnetic field is a toroidal-shaped field, vector field, and the electric is perpendicular. So let me just show you what that looks like.
Scalar is directional and magnitude, and vector is just magnitude?
Other way around. A scalar is just a number, and the vector has direction in it. Yeah. So let me look up Maxwell's.
Which I actually was underneath some really high-powered electrical lines the other day,
Yeah.
and my arms were standing up on the end, and I could feel the EMF come off of it, and I instantly I was thinking, I bet you could set up a coil right here.
You probably could.
Rob,
You probably could.
there's a guy on the mountain that has this mountain compound out by Spear, and I don't know who it is, but I was thinking, man, if I was that guy, I'd run a freaking transformer down from here and just steal electricity from it, because it's lost anyways, nobody's gonna miss it.
No, I like
It's
it.
not like you can document it.
No. So, so this is what the fields look like. These arrows are the magnetic field, and this little dot is a cross-section of these wires. And so what it looks like, so a dot means that it's coming at you, and an X means it's going away. So if I were an electron flowing through here, on one side I'm coming at me, if I'm looking from over here. Here it comes, there it goes. Here it comes, there it goes. So the electron is flowing in this helical pattern, and the magnetic field is perpendicular to it. So this is going into the page, or sorry, that's coming out of the page. This is going back into the page, and everything else in the page is perpendicular to it. So if I put a bunch of these are just, I'm just slicing now. I've just sliced through this helix.
So the repelling forces and electrical current? So for Tesla, I don't know what those are, it's not amps, it's Tesla, I mean, what's the measurement of?
Oh, sure, yeah, let's take a look.
Gauss.
Well, there's Teslas and Weavers, and if I'm not mistaken, Tesla is a scalar and Weaver is a vector, but let's check that out. Good question. I was just thinking about that this morning. So that's what the vector fields look like. So if we go back to Maxwell's equations, down here somewhere, those are the integral equations, but if we look at the differential, oh, this is a really good graph showing what the electric wave sort of looks like. So here's E. Again, that's what I just showed, and it's in bold because it is a vector. It has a direction, a flow, and the same thing with B. And again, this is beyond the scope of this course, but suffice it to say, this little thing, this is the divergence. It says when I just add up all the electrical fields around, they sum to zero. So it's a little bit like a conservation law. Same thing when I sum up all of the magnetic fields, they go to zero. This guy right here, this little cross product, is telling me that the two fields are perpendicular to each other. If I just have an electron sitting there not moving, all bets are off. You have to get the electron moving to induce the magnetic field. Once the magnetic field is there, it can move other electrons. And that's exactly what this thing is. So I've got electrons flowing in here, from the power station. The magnetic field is here. Here's your B field coming out, and it's everywhere. And it, in turn, gets these electrons flowing. So that's what this guy is. It says,
So electrical toroid stimulates the magnet, and that's what creates the repelling.
I wouldn't call it an electrical toroid. I would call it electrons flowing in a helix.
Helical electrons.
Helical electron flow.
Helical electron flow affect the magnetic.
Create a toroidal magnetic field. All magnetic fields are toroidal. They're all toroidal. Yeah.
I know, that's what he's reading back there. I got pretty weak in that one.
Yeah. So this is telling me, and it tells me, oh yeah, please, it sounds great. So this is telling me that as this electric field changes, it wiggles the magnetic field. So, and that's exactly why in all of our 60 hertz signals, there's magnets spinning around at some integer of 60 hertz. 60, 120, 180, etc. And so I guess the other thing I should mention, in this transformer, the electrons are actually getting sloshed back and forth. This was the big debate between Tesla and Edison. Edison said, hey, let's just do DC, shove the electrons in one direction. Tesla said, no, let's wiggle them. In the same way that you would take a slinky or a jump rope and you wiggle it. The rope itself isn't going anywhere. You're just whipping this mechanical wave. So in the case of electrons, you're sloshing an electron wave back and forth. The electrons themselves don't really go anywhere. In the same way that you throw a stone in a lake, you see the ripples and it looks like they're moving, but they're just kind of up and down.
What are some of the advantages you see from that?
From AC versus DC? Well, you don't have to have as big of wires.
Because of that oscillation, right?
Yep.
That wave.
Yeah, otherwise the copper wires would have to be huge.
To get anything through them.
Yeah,
Because they're all linear in that respect.
Yeah.
Trying to push all the,
Yeah.
everything at once.
yeah.
So the electrons hit the thermal radiative reading, the heat that the electrons generate heats up the magnet, or it prods or pokes. I mean, it's not like a piston, it's not like a push. It's a push.
Well, that's another thing that is also worth mentioning. So we know that the power equation, P equals IV, and we know that V equals IR. So if we just substitute V in over here, we can say that P equals IR equals I squared R. This is what actually leads to heat. So if you're running a toaster, you want high resistance. If you're running a power grid, you want low resistance.
So I is just current squared, but what would be the point? I mean, how would that be directly applied to a transform, or a?
It's not.
Okay.
It is and it isn't. So, and what I mean by that, in a transformer, you would love to have zero resistance. If you had zero resistance, your electrical grid would be 100% efficient. You wouldn't have the line losses. And so in this transformer, you don't want heat. Are there heat losses? Yeah, because the resistance is finite. And so you are always losing energy to heat, absolutely. And then just that one last thing on these equations. This is showing that as the electrical field changes, the magnetic field changes, and then the final one just says, as the magnetic field changes, so does the electric field. They're complementary. So this was Maxwell's big brain breakthrough. 'Cause he took several other, so he took Faraday's law, Lenz's law, I believe also amp, and Faraday didn't actually write these down mathematically, but he sort of demonstrated it, that, when you ran electricity through a magnet moved. So finally, to get back to your question, the answer to your question, I could also, in a solenoid, I'm just going to draw a little bar magnet. So it'll have, oh, you're the man. Thanks. Love you, man. So in a magnetic field, you've got a north and a south. You put this inside a coil, and, let's just say for now, the switch is open, but as soon as you close it, and again, I'm not being as accurate as I could be here, but as if you close it, as soon as you close it, that magnet will move. It'll come up or down, depending on the direction. And why would you do that? Well,
Turn things off and on.
yeah, you would do that if you needed some kind of mechanical actuation. If you actually had to open a valve to get gas to flow in your furnace, to get water to flow in your pipes, so you can use just the electrons that are sitting there ready to go with some kind of voltage to flip your switch, open your valve, etc.
But you convert to DC to get that. Doesn't work well with an AC system, does it? Most solenoids DC?
Well, yeah, it would be DC, yep. Because otherwise, if it were AC, the magnet would flip back and forth, yeah.
Right.
Be like
Start hammering.
Yeah.
Be like a woodpecker on
Big
the
bell?
actuators.
60 hertz.
Yeah. All right. Okay, so that's about all I wanted to go over today, because I do want to go back and look at that car. I want to get you your magnets, so you can get rocking on your turbine.
So,
Yeah. Let me see if there's anything else.
so did you get the draft that I sent you? I just want to make sure that it's in there, because I threw a draft in there.